Hello everyone, today we are going to talk about hashing and collisions. Let's talk first about the hashing concept. To store the elements of the hash table, we are going to use a list. A list is an efficient structure that allows us to retrieve elements using its position in a constant time. But in this case, if we use this structure, we have to use integers as the key. But we are not going to limit ourselves to use just numbers, but we want to use any kind of data, as for example here, where we have some shapes. So we need a hash function that maps from this data to the set of indexes in the list that we are going to use. This is the graphical representation of this. We have a set of elements, capital U, in this case the set of shapes, and we want to use a function that maps from this set to one of the positions of this list. In fact, the number of elements in this set is, we have a lot of elements in this set, and we have just a limited number of positions in the list. This means that in some cases we have to allocate more than one element in the list. This is what we call a collision. We will talk more about that later. So what are the elements that we need to implement this hash table? We need, as we have seen, a list to store the elements, because this provides an efficient way of retrieving the elements by each position. We need a hash function that maps from our data to one position in this list to get the indexes to access the elements. We will talk about this on the following videos. And a mechanism to solve the collisions that we have seen in the previous slide. We will talk very briefly about two strategies, the open addressing and the separate chaining. Let's talk first about open addressing. In this case, we have the key value pairs stored directly in the vector. So we have one pair on each position. We need a method then to determine if the position is free or not, and if this is occupied, we need a method to search for a new position. We can use different techniques, for example, exploring new positions in a linear or quadratic way. This is represented here. We have the start that gets the index 3 and then falls here. But then we have the cycle that ends also in the number 3, and we have a collision, and we have to find a new position to allocate this shape. The same with the square, and we finally allocate the square in the position n-2. This approach has some disadvantages. First, the cost of inserting elements grows drastically if the table is almost full, because we have to search many times for a new position. As we have a limited number of positions, we are only using one position for each entry, we will need to resize the list and rehash the content frequently. We will study this operation, the rehashing technique, later on this unit. We need some management of empty spaces after deleting an element, and despite all that, this strategy is widely used. In fact, Python dictionaries use this open addressing. On the other hand, we have the separate chaining. In this case, the content of each position is a list of elements, what we call bucket. The bucket contains elements that collided at that position, and this requires to store not only the value but also the key to distinguish between the elements of the bucket. This is here represented graphically. We have, for example, the triangle and the star that have collided in the position 0, and they end up in the bucket. This strategy has also some disadvantages. We still need to resize. We have more room, but eventually this will be full. The table will be full of elements, and we need to resize and rehash as well. We will talk about this later. In the case of the hashing, bad hashing will involve that the elements are not very well distributed, so we can have a lot of elements that are condensed in some part of the table. This could involve potentially long buckets, and this will impact the performance of the hash table. In this case, the key should be stored as well to identify the value in the bucket, so we need to use more space in order to allocate the same data. In case we want to study the performance of a hash table, we can use the load factor. The load factor is defined by the number of elements divided by the number of buckets. This has different meanings depending on the type of strategy that we have selected. In the case of the open addressing, this is the proportion of used positions. In the case of the separate chaining, this represents the average length of the list for each bucket. This will reflect how long are the buckets in general, so this will give us information about the state of the table. In fact, the efficiency of the hash table depends on these two concepts. First, the quality of its hash function, because better hashing involves less collision, better distribution of the elements, and its load factor. In this case, the higher the load factor, the longer the buckets, as I've mentioned before. And this is also related to the number of collisions. We have to ensure that the load factor is under certain threshold. We will talk more about that later on this unit. Thanks for watching, and see you in the next video.